The purpose of today's lesson is to introduce you to the concept of the mole, as well as to introduce you to the procedure behind the concept of stoichiometry. In order to begin, we need to consider a single atom of carbon. So on this scale, this itty bitty teeny tiny scale that I've drawn, you can tell it's really small because it's behind a magnifying glass. I have placed a single atom of carbon. And we know based on our last lesson that a single atom of carbon on average would have an atomic mass of 12.011 AMUs, or 12.011 atomic mass units. Now we do know that no single atom of carbon actually has a mass of 12.011 AMUs, but it is the average, or the weighted average, of the atomic mass of all of the atoms of carbon. We are going to use this average atomic mass in our discussion today. What I need you to picture now is taking a lot of these atoms of carbon, and we're going to blow them up onto a macroscopic scale and start to pile them up on our normal balance. So we're just going to keep adding more and more and more and more atoms of carbon, and we're going to get them closer and closer together until they really create a nice sample size. Now you might wonder, when should we stop piling these atoms of carbon up? And the answer is, we actually do have a goal. We want to picture the amount of carbon atoms that would be required to have the same mass, 12.011, but instead of being weighed in atomic mass units, we want this to now be weighed out in much more useful units of grams. So again, we had a single atom of carbon. We realized it weighed on average 12.011 AMUs. So then we took more and more and more of these atoms of carbon and we piled them up until we got a pile that had a mass of 12.011 grams. The same number as the atomic mass, but now weighed in grams instead. The pile that we have just created, this collection of atoms, is known as a mole. So a mole is a collection of atoms, or really any representative particle, that has a mass that's equal to the atomic mass, the one listed on the periodic table, but instead of being measured in AMU, it's now in grams. So then the question is, how many atoms of carbon would we need to pile up in order to get 12.011 grams? And that's where this idea of a mole really becomes useful, because it turns out that in order to get a pile of carbon with a mass of 12.011 grams, we need to pile up 6.022 times 10 to the 23rd atoms. This number is known as Avogadro's number. And this number is the same regardless of which element we're looking at. So if instead of carbon, we were looking at an atom of aluminum, instead of having an atomic mass, or an average atomic mass of 12.011 AMU, it would have a mass of 26.98 AMUs. That's on the periodic table. 1 mole of aluminum would then weigh 26.98 grams. Again, the number from the periodic table, except measured in grams instead of AMU. However, even though the mass would be different if we were looking at a different element, the size of the pile, the number of pieces, would still be the same. It would still be 6.022 times 10 to the 23rd atoms. 1 mole is a unit, kind of like a dozen. It's a count. So a dozen of anything is equal to 12 of that thing. A mole of anything is equal to 6.022 times 10 to the 23rd of that thing. Usually the things we're counting with a mole are representative particles, atoms, molecules, formula units, but regardless of what we're counting, Avogadro's number stays the same. So again, quickly reviewing our vocabulary. A mole is a collection of representative particles that have a mass equal to the atomic mass, the one found on the periodic table, but measured in grams. Avogadro's number is the number of representative particles that we need in order to make 1 mole. it's always equal to 6.022 times 10 to the 23rd. Now you'll notice I did use the E notation here, but remember that E button means times 10 to the, so 6.022 times 10 to the 23rd. When we're looking at the mass of the mole, the pile that's big enough to see, that collection of atoms, then the mass that we're looking at is really no longer the atomic mass. It's called a molar mass. So molar mass is the mass of one mole, and it's the same as the atomic mass, but now measured in grams instead of AMUs. Now the concept of the mole and the idea behind Avogadro's number are going to be used when we solve stoichiometry problems. And stoichiometry is really just a fancy term for a chemical conversion. We're going to use these two equalities in our chemical conversions. We know that 1 mole of anything is equal to 6.022 times 10 to the 23rd atoms of that element. And we know that 1 mole of anything is equal to the molar mass from the periodic table, but measured in grams. These are the equalities that we'll be using in place of the equalities of our measurements from before. One slight difference about these equalities: unlike the conversion chart that we used before, these numbers, 6.022 times 10 to the 23rd and molar masses from the periodic table, they are not exact quantities. These are rounded off. So these conversions could actually affect your total number of significant figures that you should keep. Oftentimes, the numbers we're given are still less significant figures than the ones in our conversions. So oftentimes, they really don't limit us. But keep in mind that if you had a given that had, say, 5 significant figures in it, one of these might limit the number you can have in your final answer. So let's start our conversion for the first one here. It says we're supposed to start with 2.15 grams of magnesium, and we want to know how many moles there are. Well, just like before, we start by rewriting our given, including the unit. The unit from our given goes to the bottom of our first fraction line. And then we consider our equalities. We know that 1 mole is equal to 6.022 times 10 to the 23rd atoms, regardless of the element. But 1 mole is also equal to a molar mass, and that does depend on the identity of the element. Since here we're looking for grams, we're going to need that molar mass, which means we would need to look on our periodic table. So when we look at magnesium on our periodic table, we have a 12 and we have a 24.305. This is the atomic number. We don't use that one in stoichiometry. That was just the protons. This is the average atomic mass, and that's the one that goes with grams anytime we do a stoichiometry problem. So 24.305 grams for magnesium is equal to 1 mole. Since this equals this, it can go on an equality or one of the conversion factors. Grams cancels grams, we're left with moles, which is exactly what we wanted, so we can finish out our problem. Just like before, we take our given number, 2.15, and since the number we're looking at here is on the bottom, we would divide. So 2.15 divided by 24.305, that's equal to 0.088459. We can only keep 3 significant figures because we have 3 here and we have 5 here. 3 is less than 5, so we keep 3. Remember, the leading 0 is not significant, so our final answer would be 0.088, and it would round up to a 5. 0.0885 moles of magnesium. For our second example, we're starting with moles. So we rewrite our given, including our unit. The unit from the given goes to the bottom. And now we look at our equalities and say, where do we have the mole? Which, by the way, you might notice, mole, M-O-L-E, is abbreviated using M-O-L, still mole. We can't go any shorter than that because then we get into other units. So really, if you want to abbreviate the word mole, you can just drop the E. Both of our equalities have 1 mole. So we know that a 1 is going to be on the bottom here, but we really could use either one of these on top since both of them were equal to 1 mole. And when you have a choice like that, you really should look and see what your goal is and see if one of your equalities gets you directly to that goal, which here Avogadro's number will do that for us. So we have 0.584 moles. The mole cancels the mole, and now we have Avogadro's number, which is in atoms on top. Since we want atoms, we're finished the problem, and we grab our calculator again, and we type in 0.584, and this time it's a multiplication problem because the number's on top, times 6.022. Use the E button for the exponent of 23. We hit enter. We check our sig figs. This has 3, this has 4. The 1 is a full number, so we don't actually use that to limit us. So 3 versus 4, we're going to keep 3. So that's 3.52. The 1 would round to a 2. And back here it says E23, so we need to include that as well. So that's 3.52 times 10 to the 23rd, or you can write it as 3.52 E23, and your unit is atoms, which you can abbreviate with an AT. Now you might notice that each of these problems were solved in one step. There was only one of the two equalities needed. And the reason that that's the case is because somewhere in each of those problems, we were using the term mole. Mole is in both of these equalities, so if you have the term mole as either your given or your want, it's only going to take one step to get there. Our last example here starts with atoms and goes with grams. And since we don't have the term mole written out, that's actually going to indicate to us that we're going to need both of our equalities. This is going to be a two-step conversion instead of just one. We still start by rewriting our given, including our units. The unit from the top goes to the bottom. Atoms goes with Avogadro's number, and that's equal to 1 mole. The unit from the top goes to the bottom again. And now we're trying to get to grams. So to go from moles to grams, we need this second equality. The 1 is again with the word mole, and the molar mass in the periodic table is what we use for grams. So we look up carbon, and carbon's molar mass, we actually knew from before, is 12.011 grams. So in our calculator this time, we're going to take the 1.62 times 10 to the 24th, divided by Avogadro's number, since it's on the bottom, and then multiplied by the molar mass. Since there's 3 significant figures here, 4 significant figures here, and 5 significant figures here, we're going to keep the smallest, or the 3 significant figures. So on our calculator here, we've got 1.62 E24th divided by 6.022 E23rd times 12.011. And that gets us our final answer, rounded to 3 significant figures, of 32.3 grams. So again, stoichiometry is just another way of saying a chemical conversion, and for now, we're limited to just these 2 equalities. Those 2 equalities are really based on our understanding of the term mole. And a mole is equal to either Avogadro's number, and in that case, your unit would be atoms, or 1 mole is equal to the molar mass, and in that case, the unit is grams. If you have any questions, please don't hesitate to reach out. Otherwise, you can move on to the next activity.